Hi, in this video we will solve problem 2.22 from the book Heat Transfer J.P.Holman 10th edition. Here the statement of the problem. A 1 mm diameter wire is maintained at the temperatures of 400 centigrade and exposed to convection environment at 40 centigrade with convection heat transfer coefficients of 120 watt per meter square centigrade. Calculate the thermal conductivity that will just cause insulation thickness of 0.2 mm to produce a critical radius. How much of this insulation must be added to reduce the heat transfer by 75% from which would be experienced by the bar wire. So this is the bar wire, and then insulation is provided up to its critical radius. So its internal dia is Ri and its outer dia is R0. Remember, the R0 is equal to critical radius because that is provided in the statement. So this is the first condition, and the second condition, it's a we need to find the thickness of the insulations so that the heat reduction is taken place up to 75% from the bar wire. This is the bar wire. In this case, the maximum heat transfer from this bar wire will be takes place because there is no insulation provided. It's obvious. Okay, come to the data. So internal dia is 1 millimeter. So it means then Ri will be equal to Di divided by 2. So we will get 0.5 millimeter. So this 1 divided by 2 will get 0.5. So convert into meters, minus 3 meter. Milli means 10 to the power minus 3. Maintained at a temperature of 400 centigrade. So this inside temperatures, this is Ti, and that is given, that is Ti, and that is 400 centigrade, and exposed to in convection environment at 40 centigrade. So the environment temperatures, that is T infinity, that is 40 centigrade. So the T infinity, that is 40 centigrade, that is, and the convection coefficients of the environment is 120 watt per meter square centigrade. So we need to calculate thermal conductivity that will just cause insulation thickness of 0.2 millimeter to produce critical radius. So as I already said, so the insulation that is provided over this wire, the insulation is equal to its critical radius. So we can say that R0 is equal to RCR. Critical radius, this subscript CR represents critical radius, and that is equal to A by H. And what R0? R0 is equal to this Ri and the thickness that is provided. So Ri plus thickness of the insulation that is provided. The thickness of the insulation is 0.2 millimeters. So Xi, thickness of insulation, is 0.2 millimeter. So to convert into standard form, that becomes 0.2 multiplied by 10 to the power minus 3 meter. Okay, so look at these two equations. K by H will be equal to R0, and R0 is equal to Ri plus Xi. So this Ri plus Xi is equal to K by H. Okay, so what is Ri? That is 0.5 multiplied by 10 to the power minus 3, and what is thickness in that is 0.2 multiplied by 10 to the power minus 2. Sorry, 0.2 multiplied by 10 to the power minus. There's no requirement because it's a calculated thermal conductivity, so it is unknown. So that is K divided by H. H is 120. So we will get here 0.7 multiplied by 10 to the power minus 3, K divided by 120. So multiply this 120 with this value, you will get the K, thermal conductivity of the insulations that is provided. So So you will get that the value is 0.084 watt per meter centigrade. It is the thermal conductivity of the insulations that is provided over the wire. So in the second condition, it said that the heat transfer by 75%. So reduction in heat transfer occur by 75% that can be experienced by a bar wire. It said that if we applied such insulations or this bar wire such that the heat reduction is reduced by reduction in heat transfer is taken place up to 75%. So it means that only 25% heat transfers will occur, and this 75% will be stopped by this insulation that is provided. So if you are reducing the heat transfer up to 75%, at what extent you will provide the insulation thickness, and that is also our requirement in the second conditions to calculate. Okay, so let's come to its resistance network diagram. So first, if the heat transfer takes place from insulations and then the environment conditions, heat transfer will occur. So this mode of heat transfer is conductions and then convection. So the inside temperature is Ti, this is Ti, and then conduction heat transfer occur, then convection heat transfer, and then the environment temperatures will reach. So the conduction resistance that is offered to the heat transfer in the cylindrical form is equal to ln R naught divided by Ri divided by 2 pi L, and the convections, this is, we can say, R1, this is R2, this is resistance R1, resistance R2 that is offered to the heat transfer. The second heat transfer is convection heat transfer. So this type of resistance that is offered to the heat transfer is equal to 1 divided by H into area, the surface area of this insulated wire. Okay, so this is the resistance network diagram. I hope you understand. If you still have any confusion, you can ask in the comment sections. So without wasting our time, we will move forward. Okay, so the maximum heat transfer that can happen from this bar wire, that is convection heat transfer, and that is equal to H A and temperature difference. So what is H? That is 120. And what is surface area of this bar wire? And there is no insulation provided, the maximum heat transfer occurs. So that is the area, that is 2 pi this Ri, and length. So you have to take, and everywhere you see the length, take it 1 for the simplicity if it is not provided the data. Now just put the value and then temperature difference. So the things are very easy. Now just put the value, that is 120 multiplied by 2 multiplied by pi, and then Ri is here its value 0.5. 0.5 multiplied by 10 to the power minus 3, is L is 1, and temperature difference, that is 400 minus 40. So after simplification, you will get the maximum heat transfer that's occur with the insulations, that is 135.7 watt per meter. Now in the conditions it says we are interested to reduce the heat transfer by 75% and we are only allowing 55% heat transfer. For that condition, find the thickness of the insulations. So then our heat transfers, required heat transfer is this maximum heat transfer, 25% of this maximum heat transfer. So 135.7 multiplied with 0.25. So we'll get the heat transfer, that is 33.93 watt per meter. So this is the heat transfer that takes place when the insulation is provided. Okay, now look at this resistance network diagram. Our heat transfer is equal to temperature difference divided by resistance R1, resistance R2. Remember this area, this surface area when the insulation is provided is equal to 2 pi, that is R0 is equal to ln R0 divided by Ri divided by 2 pi KL plus second resistance 1 divided by H. Output value, that is temperature difference, is 400 ln R0 divided by Ri. Ri is 0.5 multiplied by 10 to the power minus 3, that is given in the statement, and divide with 2 pi. A value is 0.084, take L as 1 plus 1 divided by 2 pi 120 and then R0, and this whole value is equal to the heat transfer, and that is equal to 33.93, and we are interested to find the R0 value. So for this we will write this whole equations in calculators and then we will solve it for this R0. So let me open the calculator for you. Oh yeah, in order to write these equations on calculators, press this button, write the values. Temperature difference, that is 400 minus 40 divided by, press again this ln R0 divided by Ri, so this is ln, press this. What is R0? R0 we need to find, so for that we put x value on the display, so press this alpha and then press this, so it will activate the x value, so x. Now what is Ri? That is 0.5 multiplied by 10 to the power minus 3, so it means I can write 5 multiplied by 10 to the power minus 4. Next is the value is 2 pi multiplied by 2 shift pi multiplied by 0.084. Next one, then I press again this math button, so and then there is one value, so this one denominator is 2 shift pi and multiply with 120, and then again we have the R0 value, and this is alpha equal, that is 33.93, and then shift solve for x. So after solving these equations on calculators, the x value you will get 0.1349. So after rounding up above, the r naught value is 0.135. R naught value for solving these equations on calculators, the R naught value is 0.135 meter. Convert that into millimeter, just multiply with 1000, so you will get R naught, that is 135 millimeter. And we are interested to find the thickness of the insulations when there is a reduction in heat transfer is 75%. That is our concern. So the thickness of the insulations is equal to is equal to R naught minus Ri. So what is R naught? That is 135 millimeter minus Ri is 0.5 millimeter. So after subtractions, you will get the thickness of the insulations, that is 134.5 millimeter. So this is the thickness of insulations that is provided on the bar wire in order to reduce the heat transfer up to 75% and allow only 25% heat transfer from the wire. Okay, so I hope you understand. If you still have any confusion, you can ask in the comment sections. Thank you so much. If you haven't subscribed to my channel, please subscribe.